You often hear that nothing can escape a black hole, that once something falls past the event horizon, it is gone forever. But according to our best ideas about quantum physics and gravity, that is not the full story. In a very quiet, very subtle way, black holes can leak. They can lose energy, shrink, and eventually disappear. This slow leak is called Hawking radiation, after the physicist Stephen Hawking, who first worked it out in the 1970s. To understand it, we have to zoom in to the region right outside the event horizon. In quantum field theory, empty space is not truly empty. It is full of fields that are constantly fluctuating. We sometimes describe this as pairs of particles and antiparticles appearing and annihilating too quickly to observe. Near the event horizon, the strong curvature of space-time changes how these fields behave. One way to picture it, a simplified story but a useful one, is this. A particle pair pops into existence right at the edge of the horizon. Normally, they would meet again and annihilate, returning their energy to the vacuum. But the black hole's gravity can separate them. One member of the pair falls in, the other escapes to infinity and shows up to a distant observer as a real particle, a piece of radiation coming from near the black hole. From far away, it looks as if the black hole is slowly glowing, very faintly, as if it had a temperature. And in a deep sense, it does. A black hole emits Hawking radiation as if it were a hot object with a certain temperature set by its mass. The smaller the black hole, the hotter it is. The larger the black hole, the colder. For the black holes we see in the universe today, that temperature is incredibly low. But over immense stretches of time, this faint glow has enormous consequences. It means black holes do not live forever. Given enough time, they evaporate.
Let's look more closely at what Hawking radiation does. From far away, a black hole behaves like a hot object, with a temperature inversely proportional to its mass. Double the mass, and you cut the temperature in half. Make the mass 1,000,000 times larger, and the temperature drops by a factor of 1,000,000. For a black hole with the mass of our Sun, this Hawking temperature is much colder than the cosmic microwave background, the leftover glow of the Big Bang. That means our Sun-sized black hole would actually absorb more radiation from the universe than it emits. In today's cosmos, it would be gaining mass rather than losing it. Only when the universe expands and cools so much that the background radiation drops below the black hole's own temperature does the direction reverse. At that point, the black hole starts to lose energy faster than it gains it. The Hawking radiation bleeds away its mass. As the black hole shrinks, its temperature rises, so it radiates even more strongly. This creates a feedback loop. Smaller mass, hotter black hole, faster evaporation. Most of its lifetime, the black hole changes almost imperceptibly. For a black hole with the mass of the Sun, the evaporation time is far longer than the current age of the universe. For a supermassive black hole, millions or billions of times the mass of the Sun, the evaporation time is even more extreme, so long that we can barely attach words to it. But as you reach the final phase, after unimaginable ages, the pace accelerates. The black hole gets hotter, brighter, and smaller all at once. In its last moments, it would go out in a burst of high-energy radiation, releasing what is left of its mass in a very short time. A lifetime of near silence, ending in a brief final shout.
So, when does all of this happen on the timeline of the universe? Right now, stars still burn, galaxies still form. Black holes are being created all the time in supernovae, stellar collisions, and galactic mergers. For the moment, they are not dying. They are feeding, growing, and shaping their galaxies. But if you fast forward far beyond the lifetimes of normal stars, you reach an era where gas is thin, star formation slows, and most ordinary matter is locked into stellar remnants and black holes. The universe keeps expanding. the cosmic microwave background cools, its temperature dropping closer and closer to absolute zero. Eventually, in the deep future, the background radiation becomes colder than the Hawking temperature of many black holes. That is when their slow evaporation really begins to matter. One by one, over absurdly long timescales, black holes start to lose mass instead of gaining it. Most of the normal matter in the universe will have already fallen into them. Galaxies will be dim, then dark, their stars gone or burned out. In that era, black holes are the last major structures left. They carry almost all the mass and almost all the information about the universe's past. The cosmos will look sparse, quiet, and mostly empty, with isolated black holes drifting in an ever-expanding darkness. And over even longer times, those black holes will start to fade. What does it look like when a black hole finally dies? For almost its entire lifetime, it radiates incredibly slowly. A supermassive black hole could take far longer than 10 to the 100 years to evaporate, a number so large that it dwarfs all familiar timescales. But as it shrinks, its temperature rises. Near the end, it becomes much hotter than the background universe. It emits not just low-energy photons, but higher-energy radiation, X-rays and gamma rays. Its mass drops faster and faster. In the very last fraction of its life, the emission could be intense, brief, and violent, a final outburst where the remaining mass is converted into a spray of energetic particles and radiation. After that, there is nothing left of the black hole. No event horizon, no singularity. Just an expanding cloud of particles and an almost perfect vacuum. By the time the last black holes have evaporated, the universe will be extraordinarily old. There may be no stars, no galaxies, and no easy way for new structures to form. The cosmos will be cold, dark, and nearly empty, a thin mist of low-energy particles spread across a vast space. In that sense, Hawking radiation is the mechanism that writes the final chapter for black holes, and perhaps for structure itself. Black holes begin life as engines of extreme gravity, powering galaxies and swallowing stars. They end as faint embers in the deep future, whispering away their mass into the cold. And in their disappearance, they remind us that even the most extreme objects in the universe are not truly eternal.